In section 2.9, we're going to continue on with our concept of looking at bases, and we're going to transition that into talking about dimension and, in particular, rank. So we looked at bases in the last section, and we saw that if H is a subspace, it can have a basis. Now, obviously, we saw in the last section that bases aren't actually unique in that there can be multiple bases for the same subspace. All right, but it turns out that there's a really nice property of a basis. So let's assume I have a basis for a subspace H. Now we know that if this is a basis, it has two properties. The first is that the span of the basis is H. And second is that the elements of the basis are linearly independent. Now, what's this mean? Well, first off, since it spans H, if you take a vector in H, you can always write that vector as a linear combination of the basis elements. So that's what span means. Second, because of the linear independence, this way of writing x is going to be unique. In other words, if you can write x as c1 times b1, c2 times b2, c3 times b3, where c1, c2, and c3 are real numbers, then there's no other real number combinations that can get you back to x. So the linearly independent set guarantees that this expression of x is going to be unique. So what we can do is we can create something called a coordinate vector. So for each vector in H, we can create a coordinate vector of x relative to basis b. So again, we're going to assume we have a basis, we're going to assume we have a vector. We know it can be written uniquely as x equals c1b1 plus c2b2 plus c3b3. So we can write the coordinate vector of x relative to basis b as just c1, c2, c3. Okay, the coefficients of b1, b2, and b3. And the notation is going to be this. A vector where I usually have x relative to basis b is equal to c1, c2, c3. Notice order is going to matter. So we're going to make sure our basis, we're always going to call the first item in our basis element 1, the second item basis element 2, and so on and so forth. So this is the idea of a coordinate vector. And what we're saying in the last slide is that if x is an element of H, of the subspace H, then this coordinate vector is going to be unique and it's also going to exist. So it's going to exist and it's going to be unique. So here's what we should do. Let's try to find the basis coordinate vector for vector x given the following basis and the following vector x. All right, if you want, push pause, try to do that, and I'll come back and do it as well. All right, so let's go ahead and do that. If you didn't do it, if you can't figure that out right now, that's fine. Let me show you once, and then we can do a couple more examples. All right, so what we'll do, we want to, essentially the whole thing comes down to writing x as a linear combination of my two basis elements. All right, so writing x as a linear combination of these two basis elements means that Well, the quick way to do that is to create a matrix equation where our matrix, I guess I can write that as B for basis element matrix times C1, C2 has to give me my vector X. Okay, and so if I can solve that equation, then we're good to go. All right, so let me start. We're going to create a matrix which, well, I'm going to just go ahead and create the augmented matrix. And the augmented matrix is going to be a 3 by 3 matrix. The first two columns are going to be your basis vectors, and the last column is going to be your x vector. So you go here 1, 0, 9. We're going to call that B1. My second vector 2, negative 1, 3. And then my vector x, which is negative 5, 4, 15. So basically, again, what you're trying to do is you're trying to find a linear combination that works. Now, I will say this, if x is not in your subspace spanned by this, well, what's going to happen with this augmented matrix? You're going to get a no solution. But on the case where you do get a solution, you should get a single unique solution. So let's go ahead and test that. And to test that, the quick way and easy way to do that is to go to our calculator. Now, I've already done this in my matrix menu. Again, second matrix, go over to edit. In for matrix A, I've already put in 1, 2, negative 5, 0, negative 1, 4, 9, oops, 9, 3, 15. And so I'm going to go back to the home screen and then go to matrix, edit math, row reduced echelon form of our matrix A. And sure enough, we get a single solution. Now, what this means is that C1 is equal to 3 and C2 is equal to negative 4. So again, C1 is 3, C2 is negative 4. And so what we would say is that the vector, I gotta look for my basis, with respect, my coordinate vector with respect to that basis of vector x is the vector 3, negative 4. All right, so that's what we'd say. So the vector, coordinate vector with respect to basis b for vector x is 3, negative 4. All right, so essentially we're solving the equation where the basis elements are in my matrix and my vector is my result vector. So I want you to push pause on the video and try this one on your own. All right, so hopefully you went ahead and did that and figured that out. So let's go through that. So we have this basis. There are 3 elements in our basis, and we have our vector x here. Now, if we're going to create a matrix equation, I want a linear combination of these basis elements to be multiplied times this vector. Notice that, again, I didn't mention this last time, but these are 4-dimensional vectors. Right now, I'm using 3 elements in my basis, so my C1, C2, C3, I'm going to have a three-dimensional vector to multiply by. So since I have 3 elements in my basis, I'm using a three-dimensional vector. And we're going to create the augmented matrix that looks like columns are the basis elements until we get to the last one. And the last one there is the constants, the x vector. One thing I will just mention, notice that I am keeping the columns the same. So I'm calling this first column my basis element B1 so that it is going to be associated with the C1. And if I do that, I better make it the first column of my matrix. All right, so that's what I tend to do. Now, when you go ahead and row reduce this matrix, what you get is, well, it looks like a 3 by 3 identity with 4, 7, -2 on the right, and then a row of zeros. Again, this is the augmented matrix, and this one does give me a solution. It says C1 has to be 4, C2 has to be 7, and C3 has to be -2. So to answer the question, I thought I had that, yep. The vector x written with respect to b, we're going to get 4, 7, and -2. All right, so that's my coordinate vector of x with respect to basis beta. All right, so now that you've done that, we've done that a couple of times, I want you to do one more on your own. I want you to take a look at trying to find this, the coordinate vector with respect to this vector x. Notice we're using the exact same basis elements here. So go ahead and push pause on the video and try this problem. All right, so hopefully you went ahead and did that. If you don't, make sure you do. Okay, so here it is. We are going to take the same basis. My new vector is 0, 8, 10, -2. So again, I think about, okay, how do I make linear combinations of these 3 items to give me x? Think matrix multiplication. That sets up the following augmented matrix, where again, each column, we have basis elements. This last column is the x vector. So we row reduce that, solve it, and it says, well, the first number has to be 2, the second number has to be 0, third number has to be -3. If this vector is going to be multiplied times my basis elements to get the vector x. So 2, 0, -3 will be the coordinate vector of x relative to basis b, or basis beta, however you like to say that. So 2, 0, -3 is our answer, the vector 2, 0, -3. Hopefully this all makes sense. I know I'm going through it fairly quickly, but the key things there are in the setup, b times a vector equals x. The one thing I do want to say is don't forget that there are certain times when you're going to have to, in order to row reduce, sometimes you have to add in some dummy columns of all zeros. All right, so we've seen that before. Now I've mentioned this, I think I mentioned this in the last section, I definitely mentioned it earlier, but when I say we want a basis for a subspace, it turns out each of the subspaces, that's the non-zero subspaces, so each of the non-trivial subspaces actually has infinitely many bases. So if you think about the span of 2, 1, 3, the only way the span of 2, 1, 3 is just a constant multiplied times 2, 1, 3, right? That's all vectors in 2, 1, 3 are going to look like a constant multiplied times 2, 1, 3. So the obvious basis is just the set itself containing the single vector 2, 1, 3. But it turns out that if you can write a vector as a constant times 2, 1, 3, it can also be written as a constant times 4, 2, 6, because these are just scalar multiples of each other. And also, it can be written as a constant times -2, -1, -3. Be more specific with just looking at this. So again, we say h is the span of this single vector, and that obviously means that this single vector would be a basis, and I should say this set containing the single vector would be a basis for h. Now, what this h is, the span of this, it means that every single element of h can be written as a constant times 2, 1, 3. All right, for example, the vector 28, 14, 42 can be written as a constant, in this case 14, multiplied times 2, 1, 3. So 28, 14, 42 is in our subspace H. However, 28, 14, 42 is also just 7 times 4, 2, 6. And you can see what we did. We went from 14 to 7 because each of the entries, if I want to go from 2, 1, 3 to 4, 2, 6, I just need to double those. All right. So in other words, 4, 2, 6 is just a scalar multiple of 2, 1, 3. It's a scalar of 2. So that means if you divide this coefficient by 2, divide 14 by 2 and get 7, well, 7 times 4, 2, 6 is going to give you the exact same vector you got out by multiplying 14 times 2, 1, 3. Now this can be done for any vector we want. If I multiplied -3, or excuse me, any scalar that we want, if I multiply -3 by 2, 1, 3, you're going to get the same thing as if you multiplied -3 over 2 times 4, 2, 6. All right? So basically, we can always do this trick no matter what vector we've chosen in H. And that means that 4, 2, 6 times a scalar can give you any vector from H, which means 4, 2, 6. I should say the vector 4, 2, 6 is alone in a set is a basis for subspace H. And we could do the same thing with like a -2, -1, 3. In fact, any scalar times 2, 1, 3 would form a different basis. Similarly, you could check that if we were dealing with the span of the first two elementary vectors, 1, 0, 0, and 0, 1, 0 from R3, that obviously the two elementary vectors themselves would be a basis. But it turns out this is another basis. It's not just a scalar this time multiplied by a vector, but you can show by row reduction that these two vectors would in fact row reduce to this one. You could also show, another way to show this is that notice that the last entries are both 0. So any linear combination of these two is going to look like something in the 1 spot, something in the 2 spot, and then a 0. Well, you can also show that each linear combination of this, since 0, 0 is here, are going to have something in the first spot, something in the second, and then 0. And so anything that's solvable with this basis, any matrix equation which is solvable using this first basis is also solvable using this second basis. I said that poorly. Don't think about the row reduction. The row reduction is a little bit weird, but that's what it is. All right. So it doesn't have to just be scalar multiples. That's the whole point of this. So they don't have to just be scalar multiples. It turns out that each subspace has infinitely many bases. Now, while there's infinitely many different bases for each subspace of Rn, the really nice thing about any two bases for a subspace is that they have to have the same size. So in other words, if there are two vectors in basis 1 for H, then in basis 2, there are also going to be two vectors. If there were 10 vectors in basis 1 for H, then in basis 2 for H, there's going to be 10 vectors. All right, and you could have seen that in our two examples, right? In our two examples, when I had 2, 1, 3 as a basis, notice the other basis, the other two bases that I chose also had a single vector. In this example, we have a basis 1, 1, 0, 0, 0, 1, 0. So there were two vectors in there, so two vectors in that basis. The other basis I gave you also had two vectors. Now, this allows us to translate into the idea of dimension. We say the dimension of any non-zero subspace is the number of vectors in a basis. So let me just go one back. So if this were my H, I would say that H has dimension of 2 because there are two vectors in a basis of H. And if you looked at any other basis for H, if you were looking at this differently, you'd still say it has dimension 2 because that basis would also have two vectors in it. So this H has dimension 2, this H would have dimension 1. So 1, because there are, no matter which basis I choose, there is one vector in that basis. All right. So any non-zero subspace of H is the number of vectors in a basis. And like we said, it doesn't matter which basis because they all have the same size. So that's what the dimension of a subspace is. By the way, notice it says non-zero subspace. What that means is that the subspace containing the zero vector only, that trivial subspace, is going to be unique, and we're going to say that has dimension 0. All right, so the zero subspace, the subspace that only contains the zero vector, has dimension 0. All other subspaces, the dimension is the same as the element, the number of vectors in a basis. All right, whoops. So we already found in the last section the idea of the column space and the null space of A. So let's go ahead and find the dimension of the column space and the dimension of the null space of a matrix A. Okay. By the way, if you remember how to figure out how many vectors are going to be in the basis for the column space of A, just as a reminder, we row reduced. pivot columns were indicating in the column in a basis for the column space of A. Free variables indicated that those free variables were going to create vectors which are in the null space of A. Not create vectors which are in the basis for the null space of A. So let's go ahead and do that. All right, so here's what we did to find the column space and the null space bases last time. So if you remember, in order to talk about the column space, basically what we're saying is what kind of vectors B can we create with these columns? And in order to get a basis, when we row reduced, we looked at the pivot columns. And so if you row reduce this matrix A into row reduced echelon form, this is what you get. Again, I just used my calculator to do so. Notice that column 1, column 2, and column 4 are pivot columns. That means in the original matrix, we could have put column 1, column 2, and column 4 into a basis for the column space of A, because that means these other two are sort of redundant. They can be created using linear combinations of the other columns. So columns 1, 2, and 4 would serve as vectors for the column space. So there would be 3 vectors and a basis for the column space. Let me write that down here. 3 vectors and a basis for the column space of A. So the dimension of the column space of A would be 3. Okay? Now, as far as the null space is what vectors, when you multiply times A, give you 0. Okay? And in order to find non-trivial solutions, we would have also row reduced A. So we would have row reduced A. Notice we have one free variable represented in column 3 and one free variable represented in column 5. And therefore, when you wrote your parametric solution, it's going to involve 2 different free variables and 2 different vectors. And those 2 different vectors are going to form a basis for the null space of A. So 2 free variables means that 2 vectors form a basis for the null space of A. So the dimension of the null space of A is 2. Actually, I'm going to write not equal to 3 because sometimes that gets confusing up here as well. I say is 3. The dimension is of the column space is 3. The dimension of the null space is 2. All right. So that's basically the idea of column space dimension, the dimension of the null space. We could write out what those bases are, but again, it's that's not the exercise here. We did that in the last section. Now notice how typing in dimension of the column space, dimension of the null space, that gets really old quick. So we actually have special words for the dimension of the column space, and the dimension of a null space of a matrix. So the word that's in the title of this section is the word rank. And quite shortly, rank of a matrix is the dimension of the column space of that matrix. So we calculate what the column space is, we can find the rank. Dimension of the column space is the rank. And likewise, the special word for the dimension of the null space of A is called the nullity of A. Now, our book doesn't quite use nullity this soon. It uses nullity when it talks about linear transformations, but we're going to use nullity of A. We know A can be thought of as a linear transformation, so we go nullity of A is the dimension of the null space. Rank of A is the dimension of the column space. So what I'd like you to do is take a moment, row reduce A, and try to figure out what the rank and nullity is for the following matrix A. All right, so hopefully you went ahead and did that. Let me go through this. So we have a matrix A. Again, if you're looking for the column space, we're looking for AX equals B. The column space, well, the basis for the column space, in this case, we row reduce A, we find 3 pivot columns, and that means that if you were going to create a basis for the column space of A, you would have included the vector 4, 8, 2, you would have included the vector 3, 6, 7, and you would have included the vector 4, 5, 6. Hopefully that all makes sense. So what's that mean? That means that the rank is going to be 3. So the dimension of the column space, since we're going to end up with 3 vectors in our column space, or in our basis for the column space, rank is 3. Now as far as nullity goes, the nullity is only going to have one free variable. So the nullity, or excuse me, row reduced echelon form of A has one free variable. That's going to lead a parametric solution with only one vector. So nullity is 1. Okay, let me go through just to remind you about the basis elements. So again, if you're trying to find the basis for the column space, we know which pivot columns generate whatever I'm looking for. So 4, 8, 2 would be a first basis element, 3, 6, 7 would be a second basis element, and 4, 5, 6 would be a third basis element. So 4, 8, 2. And now I forgot what the other two were now. Let's go back up 3, 6, 7. And the last column 4, 5, 6. So that would be my basis for the column space. Obviously that basis is not the only basis, but it's the easy one to get, and therefore, again, all other bases will have rank, or excuse me, have 3 elements as well. So the rank of our matrix A is 3. Now, as far as the null space, remember we're trying to get zeros over here. Again, imagine we have an augmented matrix with zeros to the right here. What this means is that, x4 would have to be 0, x3 would have to be 0, x1 plus 1.5, x2 would have to be 0, and that means x1 would have to be negative 1.5 times x2. Hopefully this is making sense. Let me write down, think about what we did as far as the general solution to the homogeneous equation. x1 equals negative 1.5 x2, and then I would have said x2 is free, and then the last two, x3 is 0, x4 is a 0. All right, so what we would have had in the parametric solution is a vector which is negative 1.5, 1, 0, 0 multiplied times x2. And so a basis for the null space is negative 1.5, 1, and then 0, 0. I did it. So this four-dimensional vector would be a basis for the null space. All right, now most of the time I'm not going to ask you for the actual basis for the column space and the actual basis for the null space. All we have to do is kind of say, well, pivot columns. How many pivot columns are there? Those are going to be the elements in our basis for the column space. Therefore, the rank is going to be how many pivot columns we have. The nullity, well, the nullity comes from how many vectors are in the basis for our null space, and the vectors in the basis for our null space are going to be equal to the number of free variables when you row reduce. So all we really have to do is examine some row reduced echelon forms, and we should immediately be able to pick up our rank and our nullity. So I want you to push pause for a couple of seconds and decide what the rank and nullity of a matrix, which is row reduced to this form, would be. Okay, so we already have a row reduced matrix. We want to find what the rank and nullity would have been for the original matrix A. All right. Well, all we have to do is kind of examine this. I'm going to talk through this. You'll notice that this first column is a pivot column. This second column is a pivot column. So whatever our original matrix A looked like, it had two pivot columns. And since it had two pivot columns, the column space of A would have two basis elements, and therefore the rank of A is 2. So the rank of A is 2. The null space, well, notice how many free variables we're getting here. 1, 2, 3, 4. We're getting 4 free variables, and therefore the nullity, well, I should say, let me go back. 4 free variables means that there are going to be 4 vectors in a basis for the null space. 4 vectors in a basis for the null space means that the nullity of our original A would have had to have been 4. All right, so rank is 2, nullity is 4. I want you to look at this one and decide the rank and nullity of this matrix A. Well, I should say not this matrix by itself, but if an A would have been row reduced to this form, what would the rank and nullity have been? All right, hopefully you went ahead and did that. You'll notice how many pivot columns we have. We have 1, 2, 3, 4, 5 pivot columns. So 5 vectors in the basis for the column space. So rank is 5. We have 1 column that represents a free variable. So we would have 1 vector in a basis for the null space. So the nullity is 1. So rank is 5, nullity is 1. Now I hope that you notice something about this each time. Every single matrix A can be split up, well, I shouldn't say split up, row reduced into a row reduced echelon form matrix. All right? That row reduced echelon form is going to have pivot columns and columns which represent free variables. Each pivot column represents a basis element from our column space. Each free variable represents a basis element from our null space. So if A has n columns, then the total rank plus the nullity of A has to be n. All right? So rank plus nullity has to be equal to the number of columns in the matrix. So you should be able to explain this. That's kind of what I was talking through. Rank plus nullity is equal to number of columns. Basically, if I were to ask you to explain this on a test, I would expect you to say something like, well, when you row reduce A, the total number of columns will be the number of pivot columns plus the number of columns which represent free variables. The number of pivot columns is the rank of A. The number of free variable columns is the nullity of A, and therefore rank plus nullity has to add up to n. Something along those lines. All right? So the rank plus nullity theorem is a big theorem in linear algebra. It's a very well-known theorem, and it basically boils down to when you row reduce A, it either has pivot columns or free variables. Pivot columns, elements of my are elements of my basis for the column space. Free variables are elements of the basis for my null space. So the rank plus nullity has to be n. Now, that was fairly obvious if we looked at our previous examples. So if you looked at your previous examples, right, here we had 6 columns, and our rank was 5, our nullity was 1. Here we had 1, 2, and also 6 columns. Our rank was 2, our nullity was 4. So 2 plus 4 had to be 6. 5 plus 1 had to be 6. And in the one before that, we had 3 as our rank and 1 as our nullity. 3 plus 1 is 4, and we had 4 columns. But we can also just kind of go through logically what could happen because of this rank and nullity theorem. So let's use logic to answer a couple of questions. Let's assume we have a 5 by 8 matrix. We could ask ourselves, well, what's the largest rank that A could have? Or what's the smallest nullity that A could have? Notice that kind of the largest rank and the smallest nullity are going to go hand in hand. All right? So what's the largest rank and smallest nullity that A can have? If you want to, go ahead and push pause on the video and think through this, and I'll explain how to find this if you can't think of it in about 5 seconds. All right, so hopefully you went ahead and did that. Now I'm going to look at this through the idea of our row reduced form of A. Remember, A was 5 by 8. So whatever is going to happen, the rank plus nullity has to add to 8 because we have 8 columns here. And if you think about it, we're looking for the largest rank possible. Well, the largest rank is how many pivot columns could I have? I could have as many as, well, 5, right? Because you can get ones on all the diagonal. You can have the first 5 pivot columns, first 5 columns be pivot columns. But notice you can't get any more than that because to get any more than that, you need extra rows. So the largest rank possible is 5. Okay. Now notice what that means about the nullity. Well, at most you can have 1, 2, 3, 4, 5 pivot columns. So the smallest number of free variables you could have is 3. So the smallest possible nullity is 3, and the largest possible rank is 5. By the way, think about what the smallest rank A could be and what the largest nullity A can be, or A could have, if we had a 5 by 8 matrix. So what's the smallest rank? What's the largest nullity? Hopefully you got that. Now this one's a little bit tricky, a little bit of a trick. Think about a 5 by 8 matrix. If I want to try to get the smallest rank possible, I basically want no pivot columns. So basically I make everything 0. No pivot columns at all. And that is possible if our matrix was all zeros. All right, so imagine a zeros in every spot. Zeros in every spot possible would give us no pivot points. So that's always going to be your smallest rank. Your smallest rank possible is 0. And no matter what matrix, no matter what the dimensions are, the smallest rank you can get is always 0. You could always have the 0 matrix. So smallest rank is 0. By the way, what's that mean about the nullity? If I have no pivot columns, that means I'm going to have 8 free variables. So the largest nullity is going to be 8. By the way, this is kind of in one sense a trivial case because, again, you can always put in the 0 matrix and have rank be 0. Okay, and nullity be however many columns there are. So let's go to another example. Instead of doing a 5 by 8 matrix, I want you to answer the first question using a 9 by 4 matrix. What's the largest rank that A could be, and what's the smallest nullity that A could be? Go ahead and push pause and see what you end up with. All right, hopefully you went ahead and did that. And basically, let me go through the solutions. If you think about a 9 by 4 matrix, we have many more rows than we do columns. So if we were going to try to maximize the number of pivot columns, it would be easy to do by just putting ones along the diagonal. We'd end up with 4 pivot columns, and that's as many as we can get. So basically, the largest rank possible is in fact 4. All right. How many free variables do we have in this situation? Well, none. So we could end up with 0 for our nullity. By the way, you can make an argument that that's always going to happen when you have more rows than columns. When you have more rows than columns, the smallest nullity is always going to be 0. The largest rank is always going to be the number of columns. Notice that was not the case when we dealt with the 5 by 8 matrix. When you dealt with the 5 by 8 matrix, that was a little bit more involved. You had to figure out how many pivot columns you could have, which in our case was 5, and then that would have forced you to have 3 free variables, so your nullity would have been 3. Okay, so the largest possible rank in this case is 4. The smallest nullity is 0. All right. Now, I wanted to mention this about rank and invertible matrices. Okay? Now, let's imagine we have a square matrix, a 3 by 3 or a 4 by 4 matrix. Then the following statements are going to be all equivalent. First, A is an invertible matrix. So if A is an invertible matrix, the second statement is that the columns of A form a basis for Rn. The third is that the column space of A is, in fact, Rn. The fourth statement is that the rank of A would be n. The fifth statement is that the null space of A is the set containing the 0 vector. And then lastly, the nullity of A is 0. So basically what we're doing is we're extending that invertible matrix theorem now to include concepts of column space and null space. All right. Now this is pretty obvious when these equivalencies when you think about it. Because in earlier we had the invertible matrix theorem that says when A is invertible, then it row reduces to the identity. So if it row reduces to the identity, what we're getting, for instance, in the 3 by 3 case, if we row reduce to the identity, we end up with 3 pivot columns, which means that if you look at the equation AX equals B, it's always going to have a solution in R for no matter what B is in R3. So that means that the column space has to have a basis, which is 3 vectors. It has to span R3. And it also means that if we're looking at the homogeneous equation, well, the only solution is the trivial solution. x1 is 0, x2 is 0, x3 is 0. So the homogeneous equation only has a trivial solution. That means that the only thing that A multiplies and gets 0 is the 0 vector itself. So the null space is the 0 vector itself, which means that the nullity is 0. Remember we said the dimension of the space with the 0 vector alone is dimension 0. So because we get this row reducing, if A is an invertible matrix, then it row reduces to the identity. And by the way, if A was not invertible, it wouldn't row reduce to the identity, so we'd end up with some free variables, and that would throw the whole thing off. So all those equivalent statements would be false if A were not invertible. So this is just another way to think through the invertible matrix theorem. This is sort of, you could say, an add-on to the invertible matrix theorem. And it suffices to say that this is all comes down to the fact that invertible matrices row reduce to the identity. So I want you to push pause on the video and then answer the following 2 questions true or false, or determine if the following two statements are true or false. All right, so we are assuming that A is a square matrix, okay? It says that if each column of A is a pivot column, then A is invertible. We would say yes, this is true, because in square matrices, if it's a pivot column, then we get n vectors in our column space. N vectors in our column space means that the rank is n, and we know that that means that A is invertible. So if each column is a pivot column, then that means it's going to have to row reduce the identity. Again, we're assuming square. That would not be true if A were not square, but row reduce the identity, therefore A is invertible. This second one, if the equation has a trivial solution, then A is invertible. That is false. It's false because having a trivial solution means that A is going to row reduce and have a free variable, which is going to lead to the dimension of the null space being more than 0. So again, dimension of the null space more than 0, therefore A would not be invertible. So this statement, the second statement here, is false. So the first statement is true, the second statement is false. Okay, so that concludes section 2.9, and in fact concludes chapter 2. So in the next video, we'll be moving on to determinants in chapter 3.